910, Taylor and Maclaurin series. So we've done Taylor and Maclaurin polynomials, and we've done power series, and this section pushes them together. That's what we're doing.
Nasty.
Yeah, it's not as bad as it sounds.
Okay.
So last time we actually focused on using the geometric series to find power series. It's a very isolated, usable kind of thing, right? Like it doesn't work for everything, all right? But it worked very nicely for the ones we saw last time. We ended with using this along with derivatives and antiderivatives. So today what we're going to do is we're going to take a look at a general process for finding power series of a function. And it's also probably valuable to note that what we're doing today could be used to find those same power series that we did last time in a different way. Okay? Not necessarily as convenient when we have the geometric series as an option, but it's still possible. All right, theorem 922, this is the form of a convergent power series. So if f is represented by a power series, f of x is the summation for n equals 0 to infinity of a sub n, x minus c to the n, for all x in an open interval I containing c. Then that a sub n at the beginning has a particular form. Now, we talked about this notation, but I don't know if I wrote it quite like this. This right here is nth derivatives. Okay, so I did it with specific numbers there, like I put the function, and I put a 4, and I said that was a fourth derivative of the function, and 5, that was a fifth derivative. F with the parenthesis n is the nth derivative of c, divided by n factorial. So our function, f of x equals f of c plus f prime of c times x minus c, f double prime of c times x minus c squared, and so on. Okay, so these are the details. And then let's put it all together with a definition of what this does. So if a function has derivatives of all orders at x equals c, then this summation from n equals 0 to infinity of f sub n, not sub n, sorry, f, the nth derivative of f at c, divided by n factorial times x minus c to the n, is defined as f of c plus f prime of c times x minus c, f double prime of c divided by 2 factorial, x minus c squared, and so forth. If c is general, it's called a Taylor series. And if c is specifically at 0, it's a Maclaurin series. So Taylor series is a general name. Maclaurin series is specifically when we have it at 0. Okay, so if they actually tell you this is a Maclaurin series, that gives you more information than they do if they're telling you it's a Taylor series, because then c could be anything we wish. Okay, you ready to see how we go about using this? Okay, because Adrian is anticipating it being awful, and it's not really awful. Okay. It's really not that much different than what we've already done when we did the Maclaurin and the Taylor polynomials. It goes one step further. So we differentiate several times, and that several is ambiguous on purpose, okay? How many times you differentiate will depend as soon as you start to see a pattern developing. Okay, once you see a pattern developing, you kind of stop. So generally speaking, maybe 3, 4, 5 times you're going to do it, something like that. And you're going to evaluate them at the c value. So you're going to find f of c, f prime of c, f double prime of c, f triple prime of c, however many of them you need. And then you're going to use the sequence that you develop. I don't know why this is underlined in a funny way. I think it just got shifted. To form Taylor coefficients, where a sub n is that derivative evaluated at c divided by the n factorial. So if you're doing the fifth derivative, it's going to be divided by 5 factorial. So whatever derivative you're on, it's divided by that number factorial. And we're going to determine the interval of convergence. We'll see how that works. And then put the sequence together and simplify. So we've kind of done some of these things, but not necessarily all at the same time. Okay, are you ready? See how that works? Okay, so we've got literally one example because they all work the same way, and I'd rather you guys practice examples and have time to do that on the board. So I'm just going to do one and then let you start practicing on these. And then there's one other thing in this section that we're going to look at before we do that, okay? So we have to have, I read it, but I didn't actually specify this. Where was it? Over here where it said, where was it? I can't remember where our, Okay, I know it's here because I read it before I came in and just reminded me myself here was here. As we're doing this for these, let me just show this right here. I have to be able to take infinitely many derivatives. So these are not going to be things that I eventually get down to zero. Like they can't be polynomials in this work. Because eventually if you take a derivative of a polynomial enough times, it becomes zero, right? Like the degree of the polynomial goes down, we get zero at the end. This has to be a type of function where when we take the derivative, it's continuously finding the derivatives. You can do this sort of indefinitely, okay? I can't find where it's supposed to say that now, but it's in here because I saw it earlier. So we're going to keep working. We're going to keep doing this until we have no more, we're identifying that we have the ability to do this. All right. This function has that property, no problem, right? E to a power is always going to have a derivative. It's never going to zero itself out. So it's one of those kinds of functions. And what it says I'm supposed to do is to take several derivatives. So we're going to do this. So we're going to find the derivative and do this several times. So what is the derivative of e to the 2x?
2e to the 2x.
Yes, 2e to the 2x. How about the second derivative? 4e to the 2x. The third derivative.
8e to the 2x.
Okay, we'll do one more. If for no other reason, then we see that notation showing up there, which is a reminder to us. So what is the fourth derivative here? 16e to the 2x. Okay, everybody good with that? Oh, that's fine. Okay. And then we're supposed to evaluate this at c. Well, our c value here is actually 0. So this is technically, more specifically, a Maclaurin series that we're going to find. So take a second, evaluate all those at 0, and we're going to check back in and see that everybody has the same values. I know where it said it now. Do you want to see it real quick? The thing I was looking for, I found it. It's right here, of all orders, the derivatives of all orders. That's what the phrasing I was looking for. So it means you can continue to do this as many times as you wish. Okay, what numbers did we get here? What's f prime of 0? 2, and then f double prime? And then, okay. So if you're taking a look at this pattern, right, at some point, this is how I know I can stop. I see a 2, 4, and I didn't do 0 as well. We need to have the original one. What is f of 0? 1. Okay. So if I take a look at this pattern, what kinds of numbers do you see over here? Well, they're evens, but it's not all evens. What else? Close. You're not using quite the right word. Something of 2.
2 to the n.
2 to the n. They're powers of n, right? So everything here is a power of n. So all of these are expressed, they are expressing 2 to the power of n. And depending on what derivative I'm on will depend on whether the value is there or not. And if it's not quite 2 to the n, it could be like 2 to the n plus 1 or 2 to the n minus 1. So we want to make sure it actually works. So we'll double check that as we work through this. But this is the pattern. It's a power of n that's going on. So we're supposed to, let me get to turn the paper. We're supposed to write down the polynomial that we get and then write it in a condensed form, a nicer expression. So in particular, we have the number 1, and then we have our derivative, which was 2, and it's x minus c, which is x minus 0, or just x. And then I have 4, but the 4 is over 2 factorial, because now I'm at the squaring part, right? So this one and then is times x squared. And then I had 8, and this is over 3 factorial, and it's x cubed. And then I had my 16, and I'm at the 4th derivative, so it's 4 factorial x to the 4th. And again, the reason I'm not including a minus c here is simply because my c is 0. If my c were something else, I would include it, right? I would write x minus 2 or x plus 7 or whatever they would be, okay? And this continues, correct? Right. Now, if we were doing Maclaurin or Taylor polynomials, we would have been told how many times to do this for. The one I've done so far is 4 times, right? This is piece of 4, like when we were looking at those notations. But we talked about in that section how there's a pattern developing here, and that eventually we would want to write down that pattern in a more concise way. So there's 3 pieces to this particular situation. There's I'm using the last number of my example, or the last term of my example. There's the number on top, the 16. There's a number on bottom, that's the 4 factorial, and then there's the variable component. And we want to rewrite our summation notation to include those pieces of information. So this will start at n equal to 0, and it will go to infinity. It's an infinite series. And let's start with the x to the n. Well, this x to the n, this x to the 4th, is represented by the x to the n, right? It's going to increase every single time. So if I'm looking for the third derivative, I'm going to have an x cubed. So this is x cubed, right? So it's x to the n. The denominator is pretty straightforward as well. It's also the same as the exponent on the variable. So it's an n factorial. But that numerator, that's where that pattern came in, right? So that one is the 2 to the n. Now, this is fine. You can leave it written like this, but there is a little bit more of a condensed or simpler way to write this. Any ideas?
Smash the 2 things together.
Lovely. We're going to smash them together. Okay, so we're going to put the 2 and the x together because they're both raised to the power of n over n factorial. Now, there's nothing about that you have to do it that way, right? Either of these are perfectly fine ways of writing this, and we can go with either one of them. What's that?
Is that it?
That's it.
Oh, that's a lot than I expected.
You wanted it to be way worse. That's it. Okay, what do you think? It's okay? All right. So this is the majority, I would say. I didn't look at the actual problem sets or whatever, but this is the bigger part of this section, is being able to do this for any particular function that we're starting with, okay? Let's take a look at the secondary thing that's here. You'll like this part quite a bit. So you'll probably want to take a picture of this, and I'm going to post this in Canvas. I don't have it here yet, but there's a table right here. Okay, so let's do this real quick. I'm going to just pause, send this around, take a picture of this, because I don't have a display of it. We'll just start with Adrian, just make sure everybody gets it, and then we'll resume. Okay, so we've all looked at example 2, and hopefully all noticed that example 2 is the same as example 1, right? It's the same function. We're just doing it from a different perspective. And so this question is a different type of question that will show up in this section. And they're asking us to actually use this table, the one that you guys have taken pictures of for me now, to do this. So if you take a look at the table here shows this function that's similar to the one we're working with. It shows e to the x. And it says that e to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, correct? This is from the table. All right, so we locate the correct one that's most closely resembling our problem in the table. And then we identify that in the location of the x here, this is like a u substitution kind of thing, right? In the location of the x here, we don't have x, we have 2x. So what do you suppose we do? Yeah, we put a 2x in every location that has the x. And that's all well and good, but the reason that we're doing that is because what we can actually see then is we can actually see those powers showing up without actually taking derivatives. Right? That's the step we've sort of bypassed. We've taken something that somebody else already did, and we're utilizing it for another function that's similar enough. And so we're going back to taking a look then at our summation, n equals 0 to infinity. And we look at any of the terms you wish. We'll take this one this time. And we notice, hey, look, I've got 2x, and then it's to the power n, and it's n factorial, and we end up at the same place that we were before. Okay, so we're just utilizing those derivatives having been taken for a similar enough function earlier on, by somebody else.
That's really helpful.
It is very helpful. And even if you were asked to do it like this, you could also verify it like this, right? Now, this is it's a limited table. It doesn't include everything you could possibly encounter, agreed? But it includes quite a few things. And so it's going to include the ones they give you this question for. Wouldn't necessarily have to include everything that would be for every series you encounter, but it's going to include some of them. Okay? All right, so we're going to go back then and do the interval of convergence that Sophia asked about. We've done interval of convergence on these before. Do you remember how we find an interval of convergence when we're looking for how something converges?
Less than 1.
Okay, so what do we set less than 1?
2x.
Not quite. Where did all those stuff come from when we were looking at those details? Do you remember?
Would it be e to the 2x is less than 1?
I'm looking for it. It's going to come from the ratio or the root test. Y'all know what I'm talking about now? So when we did it in the last section, we were doing it from a geometric series test. So that's kind of what your mind is thinking about, I think, right now, is what we did with the geometric stuff in the last section. But these are not necessarily geometric series in general. And so we can go back to the ratio and the root test because those are the ones that give us those intervals of convergence and allow us to use them. So let me move this over and we'll see if we have space over on the slide. I think we do. So if I'm doing the ratio test, we do the limit as n goes to infinity and we do the n plus 1 term divided by the n term, correct? So my n plus 1 term here would be, and it includes the x, so it's 2x to the n plus 1 over n factorial. Wow. N plus 1 factorial. So sorry. And then I should be dividing it by the n factorial 1, but I'm going to multiply it by the reciprocal so that I don't have to flip it later, because I'll have to flip it eventually anyway. All of this is inside of an absolute value. And once I simplify, clean everything up, I'm going to write that it's going to be less than 1, right? I still am going to have to test the endpoints, right? So the process is still like the process has always been. Let's clean things up in here. What do you notice cleans up? Okay, so the 2x to the n plus 1 on top and the 2x to the n on bottom will just go to 2x on top. What else? It's over n plus 1. Okay, do you guys remember that? It's been a couple class periods, but it hasn't been that long ago that we were looking at these. So this is simplified now. That's very nice. You can think about the 2x being pulled out in front, right? Because that actually, with the absolute value, because the limit part only affects the n part, right? X is not going to infinity, n is going to infinity. So for the moment, just sort of ignore the 2x part. Presume there's a 1 up on the top so we can talk about it. What happens to this as the limit? What is the limit of this as n goes to infinity of 1 over n plus 1? It is 0, right? So the 2x itself can be anything, and it doesn't get affected, correct? So this limit right here goes to 0. 0 is always less than 1. So what does that mean about this interval of convergence? It converges for all values, or the interval is negative infinity to infinity. So the interval here is, honestly, there's two that are the easiest. The interval where it's everything, or the interval where it's 0 and there's just 1 point, are the two easiest. When you actually get the real interval, that's when you have to test the endpoints, right? If your interval actually goes from negative 1 to 1 or negative 2 to 2 or something like that, you have to test the endpoints. That's the least friendly one. But this interval is everything like that. Cool? All right. We have a really good amount of time to practice. Y'all ready? Let's do it.